We're dealing today with radicals, and let's look at doing a number of things with them. Simplifying means thinking of it as what the perfect square is that's inside it. That's 5 squared. And think that the square root and an exponent of 2 cancel each other out. So that means that the square root of 25 is equal to 5. Now, it's also equal to -5 times -5. So -5 squared could be an answer to this. However, as we've learned in an earlier section, we're only dealing right now with the principal root. And the principal root is the positive one. So right now we're going to accept 5 as the answer for this one, although you have to remember that it would usually be plus or minus 5, except for us doing it this way for this section. Square root of 50, well, 25 here is a perfect square. 50 is not, but you can rewrite that as 25 times 2. Now, there's a couple of ways to think of this because you're allowed to do square root of 25 times the square root of 2, or you can just leave it like this. So you could do 5 squared times 2, and then the square and square root cancel out, so you get 5 root 2. Over here, you can separate them, and then the square root of 5 is 5 and root 2. Either way, you're going to get the same answer. But notice that there is now something left in there as the square root. Okay, I'm going to highlight these correct answers. Now we'll do it with variables. Notice that in these two first examples, we had a perfect square. That was the goal we were going for, was to get a perfect square inside it. So what we need to do here is rewrite this so that the thing inside has a 2 there as an exponent. Well, we know that in exponents, if you have the same exponent, x times something, whatever this is, times that. So I can think of that as 3 and, oh, wait a second, I'm doing that. I'll finish that. If I have this, then I add these to make x to the 5th power. The other thing to do is that if I have x3 to the 3rd power squared, that's the same as x to the 3rd times x to the 3rd. Add those together and I get x to the 6th. But notice here that I have a 2. I just have to make this one a 3 so that they can multiply to make 6. So here I have x cubed. Oh, let's make that so it's much more readable. X cubed squared. So the square root and the exponent 2 cancel out, and we get x to the 3rd as the answer for this one. So if that concept makes sense, then you can do a number of steps with this. In fact, you'll be able to easily take out exponents from inside a radical sign as long as you can raise it to the power of 2 or rewrite it to raise it to the power of 2. This one, you can't make that 7 to any number to a 2nd power. You'd have to go to a decimal like 3.5, and we don't do the decimals for these. So we're keeping to integer exponents. However, watch how I handle this. X to the 6th times x. Now, I wouldn't usually put a 1 there, but I'm going to now. So what I'm doing here is I'm using this method of dealing with radicals where I'm adding them. When I'm multiplying with 2 x's here, then I add those exponents. So here what I have is 6 plus 1 is 7, or I can take the 7 and split it up as 6 times 1. That allows me then to take the x to the 6th and rewrite that. So it's x to the 3rd squared x. Now this x here is only to the 1st power, so I have to leave that there. But this one here, is to the 2nd power, and we have the radical is square root. So square root of a 2nd leaves you with just simply x cubed, except that we have x cubed, and still inside the square root, we have this x. So you have to recognize that sometimes you can take some things out, but you have to split it up first. It seems a little tricky, and maybe it is, but it still makes a big difference. You're able to solve it by breaking it up like that. So look forward to doing that in a lot of these problems. Okay, now let's do it with the next two, but now we're going to do it with cubes. It's the same concept, but we have to deal with the numbers first. So what we're going to do here, what number? I'll use red on this one. You have to play with 125 and get to the point where you recognize that that's 5 to the third power and then x to the third power. And the cube root and the 3 for the 5 canceled out, so it's 5. And the cube root and the 3 for the x canceled out, so we have this. 5x is the solution for this one. On the next one now, we have a little bit of a problem because the number 250 is not a cube root. And x to the fourth, that's not a 3, that's 4. But what we can do is rewrite it. Cube root, that is 150 times 2, and the next one is x cubed times x, because that's x to the first. I don't have to show the one, but it makes more sense. It makes more sense here if I do, so you can see 3 plus 1 is 4. Now I'm going to rewrite it again. The cube there. Oh, I just made a mistake. I wrote 150 when I meant to write 125, because 150 times 2 would have been 300, not 250. So it's 125 times 2. And 125 is 5 cubed. So now we have cubes here. So in the next part, we'll just take the 5 out. But we still have a 2 here. We have this x cubed and that x cubed. So we're going to be able to remove that x in just a moment. And that x stays in there. So we're going to have 5x, and inside the square root, the 2 and the x remain. So pay close attention to the little details of what I did with these, because you have numerous times in the problems in this and some future sections where you'll have to be doing that almost automatically. You're looking for perfect squares or perfect cubes or perfect fifths, whatever it might be. Okay, that makes sense. Fractions. Okay, now what we have to deal with here is that what's called rationalizing. You're not allowed to have a square root on the bottom. No, or cube root or whatever. No radical in the denominator. No radical in the denominator. Very important. Put stars around that. Make sure you remember it. Okay. So what we're going to do here, I'm going to split this up first, and I'm going to do y to the 8th and square root of x. Y to the 8th can be seen as y to the 4th squared. So now what we have is y to the 4th on top and square root of x on the bottom. Rationalizing is when you multiply by the square root that's on the bottom, and you do it also on top because it equals 1. So that's the key thing to that. Square root of x over square root of x equals 1. So all I'm doing is multiplying by 1. This is simply the number 1 here. But I'm multiplying by it because what happens on the top, I might now have a square root, but on the bottom, square root of x times square root of x is x. So this is considered simplifying. I can't really do anything else with it because square root of x is not x. But now I have satisfied the requirement that we're not allowed to have a square root on the bottom. And I did it by using this. The square root of x times square root of x on the bottom, but then I have to also do it on top, so it equals 1. Now, the complication in this one is really simply that I had a perfect square in here, and I had to take that out first. On this next one, I have to do that on the bottom as well as on the top. Okay, so let's do square root of x to the 7th, and on the bottom, square root of y. Get this to work. Y to the 13th. Now on the top, that's x to the 6 times x inside there. On the bottom, y to the 12 times y. Notice I'm making these even. I'm trying to make these numbers even so that if they're even, then I can divide them by 2 and make it so there's two numbers that are multiplying to make 2. So what I have here is x cubed squared x root of y to the 6th squared, because 6 times 2 makes this 12 here, times y. I think I'd like that green to be all over the 12 there. Okay. Now here, I have a perfect square there and a perfect square here. So I can take those two things out, and I have x cubed square root of x. On the bottom, I have y to the 6th square root of y. So the only part that I have to get rid of on the bottom is the square root. So that means I would multiply not by the y to the 6th, and back here I wouldn't multiply by y to the 13th either, because I can simplify and only multiply by y. Just that is enough so that on the bottom, I'm going to have y to the 6th times y, which is actually y to the 7th. On the top, I have x cubed, and if there's two square roots, we can put them together. So I'll put that as the answer here. Oh, and a little word of warning. Must combine, simplify, if possible. And here it is possible. So if you left this as y to the 6 times y, it would not be correct. Some of that disappeared here. So do a little more. Now here's one with a 5th root. All right, so let's take a look at what happens with a 5th root for this one. It's going to be the same concept, but this time instead of squares inside, we need fifths inside. So I'm going to rewrite this one first as 5th root x to the 7th. And on the bottom, 5th root y to the 13th. Now on the top one, the 5th root, I need a 5, so I need x to the 5th times x squared, because 5 plus 2 makes 7. So I'm breaking down the x to the 7th into two different ones, and I'm doing it so that this and this match. So in the next part, I'll be able to take that x out for the x to the 5th. On the bottom one, what I have here, I need a number here, so I need an exponent that can be divided by 5. So if I do this one, and now let's make that more clearly a 10. 10 is the closest to 13. That can be divided by 5 that's less than 13. So now on the top, I have an x and the 5th root of x squared. On the bottom, oh, I put a y there, and I shouldn't have put a y. That was supposed to be. Let's make that y here. So on the bottom, I have the 5th root of y to the 5th squared times y to the 3rd. And now finally, x 5th root of x squared divided by y to the 5th coming out, and 5th root of y cubed. Well, we're almost done. The problem is that there is a 5th root in here. I cannot leave any one of these fractions with exponents with a cube root, 5th root, 2nd root, any root there. I have to get rid of it. And the way to do that is going to be multiplied by a 5th root that will make a y to the 5th. If I want y to the 5th, I need y cubed plus y something. Well, 3, that's not a 0. That's supposed to mean in that box. What number would be there? Well, 3 plus 2 would make 5. So what I need is a y squared, top and bottom. Doing that will mean that this y cubed and that second, y to the 2nd, We'll now let it, so that's y to the fifth, let it become that. Let's continue down here. Equals, I'll put an equal here, so it comes down to this. On the top part, I go like this here. I have an x, and inside for the fifth root, I have x squared and y squared. On the bottom, I have y to the fifth. Then inside that square root, or cube root rather, put the 5 here too, I have a y to the fifth. And that means now that, let's just rewrite the top one. On the bottom, y fifth root of y to the fifth is just a y. And then, of course, we can combine those to make y to the sixth. X, fifth root, x squared, y squared, over, oh, not a cube root anymore, y to the sixth power. Now, admittedly, this is one of the more complicated ones that you will see, but now you see how to handle it. Look back at the steps of each of the things that I did, okay, where it was first simplifying these, getting them so I had a perfect, so breaking them apart, I guess I should say, so I could get a square here, and then taking it out, and then this was the key to the thing, where I had to rationalize by the right thing that I needed so I would get rid of the fifth root on the bottom. Okay, and that's where I needed to get a 5 here by adding 3 plus, in this case, 2. So actually, I'm going to erase that little box that looks more like a 0, and I'll put the 2 in here that I need to make 5.